So today I'm going to introduce you to another type of spectroscopic technique that might not be familiar to all of us, and yet it's becoming, such an important spectroscopic technique for chemical analysis. And so in this lecture, we're going to talk about Raman spectroscopy. And I remember way, way when we were talking about different types of spectroscopic techniques, in terms of the radiation transitions after a radiation impinges of a chemical molecule or a chemical entity, we said light can undergo scattering. And I remember mentioning, one type of a spectroscopic technique that is based on light being scattered by a chemical entity is what you refer to as Raman spectroscopy. Now, Raman spectroscopy, fairly young technique, if I would call it that. It was developed by this gentleman, Indian gentleman physicist, by that name, Raman. And he observed, that when light impinges a chemical molecule, it scatters, and the scattering has some form of chemical shift, rather frequency shift, meaning, that type of scattering is what you would call quantized, okay? Quantized, because, there is a frequency shift, that is associated with an impingement, of light, to chemical structure. And so based on that, he was able to find that he could actually see the frequency shift, and associate it, with the functional molecules or functional moieties, that are present in a chemical structure. And as such, he actually won a Nobel Prize in 1930, because of the usefulness, of this type of qualitative and quantitative, as you're gonna see, technique, that can be used for chemical analysis. And so, in fact, in the paper that he published, he called it a new or a secondary type of radiation that results, from the scattering effect when a photon impinges on a chemical entity. Now, Raman spectroscopy, just a quick overview. Remember, is a vibrational type of spectroscopy. And very important, it's very complementary to IR spectroscopy, even though, they've got very different, types of bases. This one is scattering, whereas IR sort of is absorption. But despite the fact that, they come from very different type of mechanism that is taking place, the kind of spectra, that you actually get, is fairly complementary. Now, Raman spectroscopy, is based on what you would refer to as inelastic scattering. And I'm going to explain it, in the next slide. But very quickly, inelastic scattering really means that the energy of the scattered radiation, it is different, from the incident radiation, So you've got an incident beam, maybe I'm gonna call it I0, it hits a body, a chemical species, and the radiation that is scattered, in this case, a quantized, form of scattered radiation, let me call it IS, it is scattered. The frequency of that is different from the frequency of the incident beam, and that is what you refer to as inelastic scattering, meaning, there's a differential energy change, between, the incident beam and the scattered beam, and that differential, is related to the chemical entity, that is being studied. Now, as I said, the IR and the Raman, they are both vibrational spectroscopic techniques, and they are fairly complementary in terms of, IR active molecules or chemical entities in general would be Raman inactive, whereas Raman active, chemical entities in general, they would be weakly IR active or even IR inactive, meaning, the two techniques, are fairly complementary. Now, Raman spectroscopy, is ideal, for real world analysis for a couple of reasons. One of which, is that you need very little sample preparation. And as such, you can actually analyze gases, you can analyze liquids, you can analyze solid samples, without necessarily, taking them through lots of different types of sample preparation. Remember, sample preparation, is a huge bottleneck, that is fairly costly, when you're doing chemical analysis. And so techniques that do not require a lot of sample preparation, can save you a lot of money. And the fact that, of course, you can take them to the field as well. Now, another huge advantage, of Raman spectroscopy, is the fact that, you can use it to analyze wet samples, particularly aqueous, samples, that are wet. Remember, when you're doing IR spectroscopy, water is a big problem. It tends to interfere, because of the huge, IR bands, when you're trying to analyze, samples that have got some water in them. IR is not very useful, if water is actually present. However, with Raman spectroscopy, the water vibrational signals are very, very small and very, very weak, meaning, you can actually analyze wet samples using Raman spectroscopy again, meaning it's a fairly complementary technique, to IR, because IR, you can't really use it to analyze aqueous samples because, of course, water is a very IR active molecule, and so it tends to interfere, with your sample analysis in IR spectroscopy. One big disadvantage or challenge, actually, with Raman spectroscopy, is fluorescence, and we're going to talk about it later on, where you see when you heat a source, a light source, and you impinge it, on a sample, different types of transitions would happen. Of course, absorption, but emission could also happen, fluorescence. And so fluorescence, is actually an interfering signal, with Raman spectroscopy. Because, of course, remember, fluorescence, is based on, light, being emitted, from transitions among electronic states, between electronic transitions. And so it tends to be a problem, particularly, for compounds that tend to undergo fluorescence, which would be the conjugated compounds. Now, very important, I'm saying IR is a complementary technique, to Raman. Now, Raman active compounds in general, you would find, they are symmetrical, okay? So symmetrical types of molecules, or possibly, functional groups, that have got a line of symmetry, okay, tend to be Raman active, okay? On the other hand, compounds that are symmetrical in general, tend to be IR inactive, or they've got very, very weak, IR signals. Now remember, Raman spectroscopy really is actually based on molecular polarization. And the molecular polarization, occurs in this case, when a chemical species, is actually impinged by light. And that light, of course, light is an electromagnetic, radiation. It causes, the electron cloud within the molecule, to actually shift. And that is actually, the basis of Raman spectroscopy. As I've said, sort of the rule of mutual exclusion is IR active compounds in general, they are asymmetrical, whereas Raman spectroscopic technique in general, it is very, very sensitive, towards functional groups, that are symmetrical. And again, symmetrical compounds, tend to be less in terms of IR activity. And as such, again, is a complementary technique, in that sense. And I think I've already tried to explain that, as a rule of thumb, symmetrical compounds of functional groups, tend to be Raman active, whereas asymmetric, tend to be IR active. And that's why when you're talking about, say, the greenhouse gases, if I can use that as an example, just because, climate change, a very big deal. Remember, carbon dioxide, is known as a greenhouse gas. But in actual fact, carbon dioxide, types of vibration, if at all you're dealing with a stretch, because it's a linear molecule, you would find that there's a line of symmetry, for carbon dioxide. But of course, some of the stretches, are asymmetric in the sense, you can be stretching, say, the carbon double bond or in this direction, and then you're stretching, these one in this other direction, and that way it's asymmetric. But in general, what I'm saying is carbon dioxide, has got a line of symmetry, meaning, yes, it's somewhat IR active, but it's weaker. On the other hand, if at all you've got, water, it tends to be very, very polarized, because of course you've got hydrogen there, you've got oxygen there, there's a huge dipole moment right there. And again, because of that, it tends to be very, very good greenhouse gas, especially, the water vapor. And so this guy, tends to be very IR active, right? Whereas, for Raman, because it's an asymmetric type of molecule, it tends to be, Raman inactive. And for that reason, you can actually use a Raman spectroscopy to analyze wet, aqueous, samples. Now, just to give you very quickly, a summary of the Raman vibrational shifts, for different functional groups, this table can help you on that. Meaning, if at all I've got, signals, within these wave numbers, then you can tell if at all you've got these type of functional groups, that are taking place. So in actual fact, remember Raman, is useful, for fingerprinting, just like, IR is useful for fingerprinting as well. Again, they are complementary techniques. So let me very quickly, explain, the quantum basis, for Raman spectroscopy. Now, remember, with IR spectroscopy, it's a vibrational, spectroscopy, meaning the vibrations are happening, of course, within the vibrational state of the ground level electronic state. Remember, we say that with every electronic state, you've got vibrational levels. And so with the IR, essentially, is an absorption technique, where transitions are happening within the vibrational levels, of the ground state, electronic state, okay? Now, Raman spectroscopy, on the other hand, is not quite an absorption technique. However, you need an incident beam, that I'm calling sigma in this case, and it causes, scattering that is associated with quantum transition, from the ground level, meaning electrons are being transiting from the ground level, to an excited state, which is a vibrational state that is lower, than the electronic, than the excited, electronic state. Now, it's very unusual in the sense, that those vibrational states are assumed, to be between the E1 and the E0, and as such, they are referred to as a quasi, or virtual excited state, because they are omnipresent. If at all you've got transitions that are happening in an environment of electromagnetic, radiation. And so essentially, there are sort of quantum transitions, that occur, for certain types of molecules, where those vibrational levels, they are in between those two electronic states. And for that reason, we are calling them virtual, because in reality, they are fairly different, from the typical vibrational states that are present in electronic states. So in this case, it's a bit different, that they are vibrational states that are in between, two electronic states, and as such, they are virtual. And that is what you refer to as, the Raman shift, the Raman shift. Now, the Raman shift, or within these virtual, excited states, by which these Raman shifts are taking place. Now, you can have what you refer to as the Stokes shift. And the Stokes shift, it's when you've got electrons, being excited, to this virtual state. And then when it relaxes back, it would relax and rest on an excited vibrational state, of the ground state. And this is what is really expected, that when an electron is relaxing, sort of it would relax back to an excited vibrational state. And then, of course, it relaxes back to the ground vibrational state, of the ground electronic state, using what you refer to as the radiationless relaxation. And because of that, Stokes shift, as it's called, it's an elastic, it's an inelastic type of scattering, where the emitted radiation, or the scattered radiation, if I would call it that, has got, lower energy, than the incident beam, which is sort of what is expected. And as such, you're going to see the Stokes shift, is actually often larger, than the anti-Stokes. The anti-Stokes shift, on the other hand, it's when you get the excitation using the incident beam onto a virtual state. But then when it's relaxing back, it relaxes back all the way, to the ground vibrational state. And because of that, you've got a situation where the emitted radiation is of a higher energy, than the incident beam. Now, that is a rare phenomena, and for that reason, the anti-Stokes shift, often is a smaller signal, compared, to the Stokes shift. But most importantly, the Stokes shift and the anti-Stokes shift are what you refer to as, inelastic scattering, because there's a differential, in energy. Now, you also have another peak here, called the Rayleigh scattering. And Rayleigh scattering is where you've got a situation like this, where the incident beam has got equal energy, to the scattered beam. And as such, it's not very useful analytically, because there was no energy change, due to that impingement, due to that scattering. And as such, Rayleigh scattering is really noise, because, it doesn't have any chemical information that you can actually, get out of it, because the energies are exactly the same. And so you would find Rayleigh scattering is one big noise, that is present with Raman, and that needs to be actually eliminated. And for that reason, actually, Rayleigh scattering actually causes, reduction of limits of detection, for Raman spectroscopy. And so it's actually a problem. So I hope it's fairly clear, in terms of the virtual states, and how the mechanism, of the Raman effect actually works. It's very unique, in the sense, you do not have transitions, happening up to, the electronic energy levels, but instead, a virtual state, that are in between there. Now, another type, that's what you refer to as normal type of Raman spectroscopy, so the Stokes shift, and the anti-Stokes, so essentially what I'm showing you here is a typical type of Raman spectrum. But there's what you also refer to as the resonance, Raman scattering. And this is where, the incident beam has got very similar energy, to the scattered beam with a little bit of a change. And yet, this one has got a bit of chemical information as well. All right. And this one is fairly rare, but it tends actually, to happen, although it's actually fairly rare and only common, for certain types of elements, really, and very, very uncommon, for molecules, because of course, with the molecules, you expect, there are so many vibrational levels as well. So remember, resonance is, when sort of, the incident beam is very similar, to the scattered beam, and yet there's chemical information, to be derived out of it. It's referred to as, the resonance, Raman spectroscopy. Not very common, with molecules actually. And remember also, if I may say, with the resonance, spectroscopy is a situation, where you are putting in a lot of energy, such that, the virtual states, are actually past, the electronic, and the fast excited electronic state. So again, you need higher energy, for the resonance, type of scattering to actually happen. Again, I say it, it tends to be a lot rarer. So very quickly, with the Raman spectroscopy again, you need an incident beam. Very important. It's a huge determinant, for you getting a good signal. So you need an incident beam that is very energetic. Okay. And the reason it needs to be energetic is because you can see the Raman signals are very, very small. And so you need, a fairly energetic source. Now, most of the sources that are energetic are lasers. And for that reason, you would see Raman spectroscopy almost predominantly, uses lasers, as the excitation sources. And of course, there are many different types of lasers out there, with different types of wavelengths. These two are the most common commercially, where you've got an IR laser, that can produce light at red light, at 785. And then you've got a blue laser, that can produce light around, 500 nanometers. And then, of course, you have to play with the instrument to, depending on the chemical entity that you're analyzing, to choose, the right type of laser that actually gives you a measurable, Raman signal. As I said before, because you're using, high energy lasers. Now, if at all you're analyzing molecules, ideally, remember you want transitions happening between the ground state and the virtual state, and yet you do not want electronic transitions. However, with high energetic lasers, you get electronic transitions, and electronic transitions, result into emissions such as fluorescence. And so for that reason, fluorescence, is a big problem when you're doing Raman spectroscopy, because it tends to interfere, with your very weak Raman signals, the Stokes and the anti-Stokes shift. So fluorescence, is a big problem, in Raman spectroscopic instruments, because it interferes, as I said, with the very weak, Raman signals. And so how do you deal with fluorescence? The way you deal with fluorescence is to play with the laser. So instead of using the very energetic lasers, such as the 514 nanometers, if at all you're analyzing compounds that can easily undergo fluorescence, or maybe compounds that have got a fluorophore, meaning they can undergo fluorescence, then possibly it's better for you to actually use the weaker laser line, such as, the red laser, the red laser line, which is 800 nanometers. Alternatively, you can also bleach, your sample. But of course, as you bleach your sample, especially using photo bleaching, exposing it to the UV, so that you can, of course, degrade the fluorophore. The problem is, of course, you are messing up, with your chemical compound. But sometimes it's necessary, to do that. But of course, I'm saying it's not ideal, because of course you're changing the chemical nature, of your chemical entity when you're doing photo bleaching. However, if at all you are interested, say with things like metal ligand interactions, sometimes you may be forced, to do the photo bleaching, so that you can remove most of the fluorophores that are actually present. Very quickly, in terms of the block diagram for a Raman instrument, as I said, you've got a light source. And the light source, you can see in general, it's at right angles to the detector, so take note of that, because you're looking for scattered beam, really. You're looking for scattered beam, and you do not want, the incident beam, to actually interfere, with the scattered beam, and hence why you're doing the 90 degrees angle. And then, of course, you've got the wavelength selector, which is very, very important, actually, Raman spectroscopy. Because of what I said, you've got the Rayleigh scattering, which is a big signal that has got no basis in terms of the chemical information, and yet it needs to be removed. And so Raman instruments, tend to have very good optics. And optics, of course, is what you're calling the wavelength selector here, so that you can select, the light of interest. Radiation transducers, remember the detectors that you use here is very similar to what we talked before. Things like the CCD is very, very common, or even the PMT, but the CCD, is the most common type of detector, the so-called charge cathode devices. And, as I said, you have to use the right type of optics, and often you use optical fibers, to transmit the light, from the microscope, to the monochromator and so on. And so you use the light guides, things like the optical fibers, to capture the light, so that, you do not lose any of the light, scattered light, that is the signal, of interest. Also very important, you're going to see Raman spectroscopy always, has a microscope with it, so that you can actually focus, the sample, or focus, the analysis on the sample. So in most cases, in almost all cases, actually, you've got a microscope, that goes together, with the Raman instrument. And so that way you can actually do the imaging, chemical imaging. At the same time, you're actually getting chemical information, or chemical spectra, that is coming from the specimen. So very important technique, so you can call it actually a surface technique, meaning, you can actually do the surface mapping, of your sample. And so very useful, as you're going to see later on, and you're trying to analyze, the surface of probably a material such as a nanomaterial, a carbon fiber, a textile, and so on. So you can actually get, the chemical image, how the image looks like, as well as get, the spectra. And that way you can, get lots of good information. So very, very quickly, I think I've already mentioned this, sources. In most cases, you use the laser, for the reasons that I gave, that you want a very energetic beam, so that you can actually get a fairly good signal, or Raman signal, all right? And of course, it also needs to be monochromatic as well. Now, as I mentioned, you can analyze gases, but you can also analyze liquids, and solids as well. So it's a very versatile technique in terms of you don't have to really prepare your sample. In fact, in most cases, all what you really need is a glass slide, and then you just put a sample onto that glass slide. And then you've got the microscope, you focus, the microscope on what you are interested in, and then you shine, the laser, onto the sample specimen which you've already focused, and then you can actually get, the spectra at the end. So it's a very, very simple technique actually to play with. But unfortunately, in terms of the signals, they tend to be very, very small. And there's a lot of interferences because of the Rayleigh scattering and fluorescence at the same time. And for that reason, sensitivity is always a big problem, with Raman spectrometers. Yeah, so maybe the only useful thing in this slide is just to overemphasize again that you need, very good optics, so that you can remove the Rayleigh light, which interferes, of course, with the Stokes and the anti-Stokes signal. Now, I also remember the detector in most cases, is a CCD, as well. I've already mentioned, with the Raman spectrometers, the Raman intensity line, if I can put a number on it, is about, 0.01% of the incident beam. So you can see how weak, the Raman signal is actually, because of course there's no electronic transitions. You're really dealing with a virtual, vibrational, transitions. They're very, very weak. And yet, of course, fairly useful technique as well. But of course, you can, with the resonance Raman spectrometer, which is very unique in the sense that you've got electronic somewhat transitions, the signals tend to be a little bit larger. But the normal Raman, which is this, has got very low signals. So as you can see, with the resonance, where you are transitioning electronically between electronic transitions, you tend to get, a larger, type of signal. So the limit of detection, is a lot better, compared to the normal type of Raman. The problem is, of course, with resonance, you've got this big problem again of fluorescence, that you have to worry about. Now, to solve the problem of limits of detection, people have played a lot with how to increase or to enhance the Raman signal. And so they've developed this technique called surface enhanced Raman scattering spectroscopy. And my research group, has also been developing different types of nanomaterials that can be used to enhance the Raman signal. So in general, you would see that if you take the sample and you mix it, with silver nanoparticles, for example, or even gold nanoparticles, now they tend to increase the Raman signal. And often, that is based on what people call the surface plasmon effect that often takes place, on gold and silver nanoparticles, so it's very similar actually to the MOLDI instruments, that causes, ionization, of the samples if you use a matrix. So in this case, the matrices that people use are things like gold. And because of the enhanced, electric fields called surface plasmons, then you would get excited or rather enhanced Raman effects due to the use of these type of nanoparticles. And lots of people are playing around with different types of nanoparticles, to increase Raman signals. For example, in my group, we've been using silica, silica nanoparticles, in fact, biogenic silica that we extract from phytoplanktons. And we have actually shown, that it tends to increase the Raman signal substantially. And we've submitted, that work for publication. So again, surface enhanced Raman scattering is when you use nanoparticles, to increase the Raman effect. And it's believed the reason for that is because of increased electric fields called surface plasmons, due to addition of the silver nanoparticles. As well as other type of nanoparticles, things that are sometimes called quantum dots, and so on. Big field out there, but again, substantially used to enhance the Raman signal. So you can read a little bit on your own if you're interested about SARS, which is a very common or a growing technique out there. So very quickly, in terms of applications of Raman, it can be used for many different types of applications. Remember, and I like you to really get this, is a surface technique, because you're probing really the surface of a material. And so you can actually use it, without much sample preparation. So you can analyze things like fullerenes, which are carbon 60 types of carbon allotropes out there. You can analyze different types of polymers, such as that. You can analyze small molecules such as cocaine. I think that's cocaine actually, yeah, such as cocaine. You can analyze, fibers as well. And as I said, you've got different wave numbers for different functional groups. So you can do fingerprinting of different types of fibers out there. And so for forensic, investigation, it tends to be a fairly useful technique that is complementary, to the IR. Now, let me summarize very quickly, in terms of the key summative point comparing Raman to its complementary technique, IR spectroscopy. Very, very quickly, I'm going to go here because we've already talked about it. So it's based on the two techniques, are based on symmetry of the molecule. So if at all I've got a symmetric molecules, they tend to be Raman active. If at all they are asymmetric molecules, they tend to be IR active. So remember that. So again, it's a complementary, technique in that sense. So conjugated type of compounds, they are highly Raman active. And you're going to see IR tends to have very small signals, for these types of functional groups, because they've got a point of symmetry. So again, very useful, for analysis of conjugated type of molecules. Whereas things like this, OH, and NH, they tend to be highly IR active, because of course they are polarized, there's a dipole moment, right there, in terms of the energy density, of oxygen is very different from the energy density of hydrogen. And of course, if you think about the electronegativity of oxygen compared to hydrogen, they are different, so there's gonna be polarization. And anything that has got a lot of polarization here again and doesn't have a point of symmetry, tends to be very IR active. And so again, you can see the complementarity of the technique there. Now, if at all I've got a conjugated molecule such as this, you tend to get a very big signal. The double bond of carbon, tends to have a slightly lower signal, whereas a single bond, tends to have an even smaller signal. For that reason, very useful technique to analyze the allotropes of carbon, such as graphite, carbon nanotubes, graphene oxides, and so on. So it's used a lot to differentiate those different types of allotropes. As I said before, water doesn't scatter, the Raman substantially, and so you can analyze samples that have got water in them, which otherwise would be difficult to do with the IR. Now, you can analyze samples on glass, with the Raman, whereas it's impossible to use glass, with IR, because glass tends to have a lot of OH groups. Remember, glass is silica, and silica has got a lot of silano groups, and that gives you a lot of IR bands, and for that reason, you cannot put a sample on glass and analyze it using IR, but you can use Raman with glass because Raman tends to be inactive, or glass tends to be inactive, when you analyze it with Raman. Now, Raman, you get very weak signals, and that's a problem. But also, you can analyze very small quantities, of your sample, which is a very good thing. And again, you're using a laser beam, that tends to be very monochromatic. It's laser focused, meaning, you can shine a laser on a very small type of material. So meaning even a small debris, a small particle, you can actually use Raman spectroscopy, to probe it. Now, one big challenge, with Raman, because you're using IR, you tend to have issues with sample overheating because, of course, the sample is gonna absorb the radiation from the laser. And if at all the sample is thermally unstable, lasers, can degrade also, the sample, which is a problem. So you always have to worry about overheating your samples or decomposing your samples, when you're doing Raman spectroscopy. Now, Raman spectroscopies, they are painful. You need a lot of careful calibrations because, as I said, Raman shifts are very, very low in energy. Unlike the IR, almost anything you throw in an IR spectrometer and you get a signal, a big signal. But with the Raman spectrometers, you really need careful calibration of the optics, so that you can actually get a good Raman spectra. Now, Raman spectra is very useful for analysis of inorganic systems, especially, metal, with ligands, the so-called coordinate dative bonds, I guess coordinate, dative bonds, where you've got a ligand, is an organic molecule interacting, with a metal, and you've got that type of bond that is formed between a metal center and a ligand. And Raman spectroscopy tends to be very, very good for the analysis, of those types of bonds, which tends to give you shifts, around 100 to 700 wave numbers. And this is a very busy region, for the IR. It's not useful analytically for the IR, but it's very useful, for the Raman. And as such, you can do the analysis of inorganic systems, such as, the so-called meta-organic frameworks, which is becoming a very big issue out there, or a very big area of study. For example, things like chlorophyll, you've got a metal center, which is iron, and so on. Hemoglobin, rather, you've got a metal center, which is iron, and the way it's reacting, or rather coordinating, really, with the functional groups, other functional groups. Or even chlorophyll, you've got magnesium, a metal center, and then it's coordinating, with the hydroxy groups. And so you can use Raman spectroscopy, to study those kinds of systems, which is very useful, because they tend to give you shifts around 100 to 700 wave numbers, which are otherwise chemically messy, with the IR spectroscopy. Now, Raman spectra, also tends to be less cluttered, compared to infrared, meaning it's less busy, compared to the infrared spectra, meaning it's easy to interpret that kind of spectra. And as such, you can actually use it for quantitative analysis in a lot simpler way, compared to the IR spectroscopy, which tends to be very, very busy. Unfortunately, Raman, has not been exploited as much for quantitative analysis, partly because it's fairly expensive. And the reason is because the reason it's expensive, is because of the very high quality optics, that have to be used. Because, like I said, you're dealing with very, very weak Raman signals, and so you need very high quality optics, to actually be able to detect, the Raman signals. We have a good Raman instrument now in McEwan, which we are playing with. Fairly high cost. I think it was bought for 100, 200K. Which is not a small amount of money. So it's starting to be used, for quantitative analysis. But again, other than the high cost, the signals tend to be lower unless, you try to use a so-called SARS, which is Service Enhanced Raman Spectroscopy. But again, SARS in terms of the mechanism is not very well understood. So it's still in the exploratory stage in terms of what types of matrices you can use to enhance a signal other than silver nanoparticles, gold nanoparticles, and other types of quantum dots. So in finishing, the very last slide here, remember Raman is vibrational spectroscopy, similar to IR or complementary to IR, and so it's used for fingerprinting, of chemical entities such as, similar to the IR. Is a surface technique. You can analyze gases, liquids, solids without a problem, so you don't need a lot of sample preparation, which is a huge advantage, of Raman spectroscopy. Now you have to use a laser, so that you can enhance the Raman signal. And the types of lasers typically is 514 nanometers and 785. The challenge is, using lasers that are this energetic, you have problems with fluorescence if you're analyzing materials that can undergo fluorescence. And so, as I said, SARS, is one of those emerging technique, that researchers are trying to work on so that you can enhance the otherwise weak Raman signal. Similarly, and very important, Raman you can actually capture using microscope because they almost come together. You got a microscopy connected, to the Raman. And so you can actually do imaging, of your chemical material at the same time as you're acquiring, the spectra. So you can get, both information, the morphology, as well as, the chemical signature, of your material. And finally, you can actually use Raman to analyze wet samples, because aqueous or water, tends to be Raman transparent. And also things like glass tend to be Raman transparent, making Raman a fairly useful technique out there, for analysis of aqueous samples. And that's all that I'm going to say really, about Raman spectroscopy, a fairly versatile analytical tool, that is having a resurgence actually, in the last 10 years, people are starting to find the value, of using Raman, especially because you don't need to prepare the sample for analysis, and that saves you time and money as well. However, Raman spectrometers still remain a little bit bulky though, although there are a couple of instrument manufacturers out there that are trying to produce, miniaturized type of Raman spectrometers. But because of the limitation of the optics, you tend to have very low type of limits of detection, with Raman spectroscopy.